In this activity, we are going to be learning about the powerful technique of spectroscopy. Please remember that the color of light is determined by its wavelength or frequency, and the light that we typically perceive, sometimes called visible or white light, is actually a mixture of electromagnetic radiation of many different wavelengths, typically between the boundaries of about 400 to 750 nanometers. As the arrow points, there is something called a prism, which is sort of like a pyramidal shaped type of glass that is able to separate white light into its component colors, and that is what we call a continuous spectrum. Now, how do we actually see color? When light hits a substance, three things may happen to it. We call this the incident light. Some light may bounce back. We call that reflection. Some light may go through the substance. We call this transmission or transmittance. And some light may, quote unquote, stay in. We call this absorbance. Why do substances absorb light? Well, selective absorption occurs because the frequency or wavelength of the light wave matches the frequency at which the electrons in the atoms of that material vibrate in their respective orbitals. And as we saw in class, it is possible for a substance to have an arrangement of orbitals such that light of a particular wavelength has just enough energy to get electrons excited to higher orbitals, and that causes absorbance of light. Now we can take advantage of this by building what is called a spectrometer, and what you see here is just simply like a formal sketch of how it works. We start with a light source here on the left side. Light is then concentrated and passed through a prism that we see here in the middle, that triangle shape, which then breaks up the incoming light into its various wavelengths. So what we do now is we interpose a filter or a wavelength selector, which will allow only light of a particular wavelength to go through. And that is the light that we shine through our sample solution. And then we have a detector on the other side. Now, there are two types of measurements that we can make in spectroscopy. One thing we can do is we can measure what is the ratio of the intensity of the transmitted light to the intensity of the incident light. As the diagram will show now, the transmitted light is the one that makes it past the substance, and the incident light is the one that enters the substance. Again, in this case, our substance is a solution of a particular compound. We can calculate the transmittance, T, as the ratio of the transmitted versus the incident light's intensities. Notice that although this is a ratio, we sometimes can express it as a percentage, and as the ratio would indicate, the higher the value of T means the more light is being transmitted. The second type of measurement that we can make is what is called the absorbance. And in our hands, absorbance is going to be defined as A equals the base 10 logarithm of the reciprocal of the transmittance. Notice that they're inversely related. So in other words, the higher the transmittance, the lower the absorbance. And notice that absorbance is measured on a logarithmic scale. So we typically express it without any units. Once more, the higher the value of A means the more light is absorbed. Or in other words, the less light is transmitted through the solution. Now, we can do two types of experiments here. Whether we're measuring transmittance or transmission, or we're measuring absorption or absorbance, we can ask two types of questions. Number one, what wavelength of light is best absorbed by the solution? Number two, how much light does a solution absorb depending on its concentration? So, in the first activity, we do what is called an absorbance spectrum. We're going to measure the absorbance of a solution of known molarity over a range of wavelengths, and we're going to plot the absorbance versus the wavelength. The typical graph that you get will look something like this. Notice that again, we're plotting the absorbance on the left without units versus the wavelength in nanometers. And this is for a solution whose concentration we have already measured and is known. Notice that there is a peak here, and if we look at where that peak reaches its maximum absorbance and we trace down to find what that wavelength is, we find what is called the wavelength of maximum absorbance, or for short, the lambda max. This is the wavelength at which our solution will have the maximum absorbance, and therefore any variations in the solution will be easily detected by a change in the absorbance. One interesting thing here when we do a spectrum is that, going back to the color wheel that you may have seen in art classes, the color of the solution is typically going to be complementary to the color that corresponds to its lambda max. So for example, in the previous chart, we saw that the maximum absorbance occurred at a wavelength of about 470 nanometers. We just kind of like estimated that. Notice that that falls in the blue region of the color wheel. So that means that we expect this solution that is absorbing at that wavelength to then project out a color that is complementary, which means we would expect this solution to have an orange color. Now, the other thing we can measure is the absorbance of solutions of varying molarities at a specific wavelength. And for that, we typically use the lambda max. And then we will plot the absorbance versus the molarity. When we do that for typical solutions, it is interesting that we'll find that the data points fall almost along a straight line. This is what is called the Beer-Lambert Law. It says that the absorbance of a solution is directly proportional to its concentration. In other words, A is directly proportional to the molarity. There is a general formula that we can use, A equals epsilon times C times L, where A is the absorbance. Epsilon, the Greek letter, is the molar absorption coefficient in units of per mole per centimeter. C in this case is the concentration, but we typically use molarity. And L is the optical path length. In other words, the distance that the light travels between entering and exiting the solution. For our purposes, typically these two values, the molar absorption coefficient and the optical path length, are not of our concern. We typically are working with solutions that are fairly dilute and therefore behave ideally. And so epsilon will be a constant. And we typically use a path length of 1 centimeter. And so the math there is irrelevant. We are more concerned about the relationship between the absorbance and the molarity. So let's say that we had done an experiment, a previous substance, or a previous substance that we had. Notice that we plot the absorbance on the y-axis, the concentration on the x-axis. Very important, we need to indicate what is the wavelength at which we are carrying the experiment, and also what are the units of concentration that we are using. Notice that the data points, as predicted by the Beer-Lambert law, fall along a straight line, and of course we know from algebra that the equation for a straight line is y equals mx plus b. In this case, y would be the absorbance, x would be the molarity. So if I have this graph with its equation, and now I have a solution of unknown molarity, if I can measure its absorbance, given the absorbance of that solution, I can use the equation of the line to calculate the molarity. Okay, so for this experiment, we have several objectives. In part A, we're going to prepare a test solution of cobalt-2 chloride of a target molarity. In part B, we're going to use that test solution to do an absorbance spectrum and identify what is lambda max for this substance. And in part C, we're going to take the test solution and prepare solutions of known molarities. We're going to do these by dilution. And we're going to use them to build a Beer-Lambert plot, in other words, of absorbance versus molarity, and then we're going to use that plot and its equation to determine the molarity of an unknown solution of cobalt 2 chloride. Please proceed to the next video in this series for further demonstrations and instructions. Thank you.